Hello students, hi everyone. Today we are going to do series error correction. Today we are going to discuss error correction topic. Already we have spoken error detection topics in the previous class. So today we are going to discuss error correction topics. So let me share my screen as well. Okay, now my screen is perfect, right? So we are going to start our error correction topics. Okay. So coming to this error correction topic. So here we have also two approaches to the error correction. Previously we have gone over an error detection. Now we have to go for the error corrections. Two approaches we have. One is a backward error correction. Another one is a forward error corrections. Coming to the backward error corrections, what it means it's nothing but an error detected in your stream that sender is going to be sent. It's an error. It's an error detection in a frame. The sender is also asked to retransmit the data or frame. Okay, we are going to be retransmitting as a data or frame. So here that is called as an automatic repeat request that we shortcutly we call as an ARQ. Okay, shortcutly we will be calling as an ARQ. Okay, so this is a backward error detection or sorry, backward error correction it is. So coming to the forward error correction now, it is used more redundancy in the transmitting data. When you are transmitting the data, it has a more redundancy data, not only detection, but also it's going to be detected also. Okay, here it is going to be detecting, but also to correct errors in the receiver data as well. Whenever you are sending an error, it's going to be detect the errors and as well as it's going to be correcting those errors in the received data. Means it is performing this error correction and detection. So coming to this, what are the examples we are going to see in error correction and detection, right? Sorry, means forward error correction and there's a backward error correction. So for example, for the backward error corrections are stop and wait ARQ, which is an automatic repeat request, stop and wait, and go back N ARQ and the selective repeat ARQ. These all three topics will become 1, 2, and 3. These all three topics will become in your data link control flow. Okay, so it comes under your data control flow. Okay, so now coming to the forward error corrections, it's a Hamming code. Okay, it's a Hamming code. Whenever you are hearing there's a Hamming code from the outside, it will be called as a correction and as well as a detection. It will be called as a correction and as well as a detection. They will. So, 1 second. The Hamming code this will be called as both error correction and as well as a detection. It's going to be considered as an error correction and as well as a detection. Okay. So let us see this brief explanation or clear explanation about all the topics. First, we'll be going through the forward error corrections, that is a Hamming code. Okay. So after that, we'll go for the backward error correction. So let us know this error correction process first. Before going to the process, first we need to know what are the error correction processes. So if you see here, there's an error correction process. The first we are sending as a data within k bits, that we call them as in k bits. Here, free error correction encoder is going to be added to your data. Error frame, error correction encoder is going to be adding to your k data. That will be called them as a code word. That will be called them as a code word. Okay, it's considered as an n bits. Okay, this n bits is going to be transmitted to the receiver
This whole code word is going to be transferred. This code word is going to be again performing this frame correction error correction process decoder. Okay, here frame correction frame error correction decoder is going to be performed. So it is going to be get this data. So we already learned this. If the reminder or if the data which we are transmitting from the sender to receiver, the receiver will perform the same operator, same process. When we are performing the same process, if we get the 0 1, so will be the receiver will be confirmed that the data is transmitted in correct data. If it is not done, it doesn't mention this error is not a correct data. Okay, if you have received anything, so it's not a correct data, it was transmitted. Okay, this is the process. First, the k bits. For this k bits, the frame correction, error correction encoder is going to be added to your data that we call them as a code word. This code word is going to be transmitted to the receiver. The same decoder is going to be used for your receiver. The decoder will get the same data. The decoder will get the same data. So this is the error correction process. This we call them as a error correction process. So let us see this the next one. So Hamming code. We already mentioned this. We are going to see this forward error correction. Here, first of all, it's going to be detect as error. After that, it's going to be correcting as error as well. Error correction and as well as error detection is going to be done by Hamming code. Okay. So let us see this Hamming code. It's an error correction code. It's an error correction code that can detect up to 2 bytes of errors, 2 bits of errors and a single bit error. It's going to be detect. It's an error correction method. It's an error correction method, error correction code, and it can be detect up to 2 bits of errors and then single bit errors as well. Okay. So and along with this, it uses parity bits. It uses parity bits strategically placed when the data to detect and correct the errors. Okay. It uses parity bits. It will be placed within data to detect and correct the errors. Okay. So in the same way, we have a step-by-step process how to construct the Hamming code. So let us see the step-by-step process of constructing a Hamming code. Okay. So let us start this section. Starting with an example, we'll take a small example. We'll be starting with a small example that's in encoding 4 data bits using an 7,4 Hamming code. 7, comma 4 Hamming code. Already we have learned the error correction process. How this error correction process means, we have the k bits. From this k bits, we are doing the encoder. From this encoder, that is also error correction encoder. That error correction encoder is going to be added to our code word. Right? So that code word is going to be transmitted to the receiver. Fine. So let us see this here. There's a 7, comma 4. Previously, we have not used this type of format. So in the Hamming code it was using. So we have to know what it means, right? So 7, comma 4 notation means here we are going to be used 4-bit data, 4-bit data and 3 parity bits. 4-bit data and 3 parity bits. Okay, did you understood why they have written 7, comma 4? 7 means 3 plus 4. Right? 3 plus 4. 4 plus 3. So how many we have? 7. Right? 7 comma 4 notations. Okay. So here 4 parity bits, 4 data bits and 3 parity bits they have added. So resulting in a 7-bit code word. Code word is nothing but a k bits less FEC, that's a frame, error, correction, and encryption, encoder. It's going to be added to our code. Okay, so let us see this. The step-by-step process. Have to perform this example by taking this 7, comma 4 Hamming code with the encoding of 4 data bits. Okay, so let us enter into it. Step-by-step process. We are going to see it. Number 1. So first we have to determine the number of parity bits. The number of parity bits. We have already seen this 7, 4. In a Hamming code means 4 is a data bit, 3 is a parity bit. So where the parity bits were added, there the 4 data bits is going to be added. So we have to know that the process. So first we have to determine what are the number of parity bits we have. Okay, so let us see this. What are the number of parity bits we have? So here in this Hamming code, the number of parity bits is going to be mentioned as a P. It's going to be mentioned as a P. It is determined by the relationship. What is this relationship? In this format of the relationship, that is a 2 power P greater than or equal to P plus D. P plus D. So here D is nothing but a data bit. Okay, D is nothing but a data bit. It's a 4. So what is our data? 4, right? So we are entering as a data is a 4. There's a D is nothing but a 4, right? So now we'll see this where D is the number of data bits for 4 data bits. D is equals to 4, right? So here 2 power P greater than or equal to P plus 4. P plus 4 as per this formula. So as per this relationship we have created this one, right? So now if P for P is equals to 3, we get 2 power 3 is equals to 8 greater than 3 plus 4. 2 power 3 is greater than or equals to means 2 power 3 greater than or equals to 3 plus 4. Here 3 plus 4 is an 7. 8. 2 power 3 is nothing but an 8. 2 to the 4. 2 to the 4. 4 to the 8. That's it, right? So now 8 isn't greater than 7. So now this condition is satisfied. So we can know this the number of parity bits. Now it is a 3. The number of parity bits is a 3. For P is equals to 3, we have took. Right? So thus the 3 parity bits are added to our data. Okay, now you got the clarity. First, we have to determine the number of parity bits based on this particular relationship. From this relationship, in this D is nothing but an your data bit, how many data bits we have. So from the data bit, from this data bit, so we have to find out this actual, the parity bit numbers. Actual parity bit numbers. We can directly let's say this it's a 7 comma 4. We can say this 7 minus 4 it's nothing but a 3. 3 parity bits is going to be added. This statement is not suitable for the all the problems. Okay, it may suitable for some problems, not for all problems. Okay, fine. So we have to follow this relationship for everything. We have to follow this relationship. Okay, we should not blindly go on with the shortcuts. We have to follow with the relationships only. Fine. So coming to this second step. First step, we have find out this number of parity bits. Now coming to this, determine the positions of a parity bits. We have gone through with them. What are the number of parity bits, right? So now we have to go. What are the number of positions of the parity bits? Positions of the parity bits. Okay, so let me go through with the positions of parity bits. Positions of an parity bits. Here, the parity bits are placed at the position that are powers of 2. It's going to be placed powers of 2. So, what are the powers of 2? 1, 2, 2 to the 4, 2 4 3 8, 2 4 4 16. So it will be changes. Okay. For 7 total bits, the positions are parity bit P1 position is in 1, the parity bit P2 position is 2, the parity bit P4 position is at 4. Now you got the point. So we are going to give this a powers. There I have 7 bits. 7 total bits, right? 1, 2, 3, 4, 5, 6, 7. This was not there. Okay, this was not there. We have to consider this one only. From this bit, okay, I need to take this a power of 2. 2 power 0. It's a 1. So this is the P1. This is the P1. Okay. The next power of 2. Next 2 power 0. 2 power 1 is the next power. 2 power 1 is nothing but a 2. It's 0, 1, 2. So it's going to be mentioned P2. Next 2 power 2. 2 power 2. 2 to the 4. So now we have to go through with the parity bit of 4. 1, 0, 1, 2, 3, 4. It's going to be mentioned at P4. Okay, now we got it. Now we got it. So how we have got this parity bits one? Now you got the point. I think so. Right? So now let us go to this. We have find out this positions. Right? So the data we have gone through the positions of parity bits. Now we need to know the positions of data also, right? So the remaining data will be considered as in positions of the data bit. Right? 1, 2, 1, 1, 2, and there's a 4 is gone to with an parity bits. Okay, uh, remaining are 3, 5, 6, and there's a 7. Okay, remaining 4 bits, right? So let us see this. The position, the data bit D3 is the first one, data bit of 2, D5, data bit of 6, sorry, third one is in 6, data bit of fourth one is in 7. Okay, so now let us the data bit and as well as the parity bit, the combinations will be arranged in a single day code one, in a single code one. So now you can see there's a positions and there's a contents of. We already mentioned 1, 2, 4 or parity bit. 1, 2, 4 or parity bit. 3, 5, 6 and 7 or data bit. 3, 5, 6 and there's 7 of data bit. Okay. So now it was clear. Right. So now we have determined the positions of parity bits and as well as the positions of data bits. Okay. Now coming to this third one. Place the data bits. Place the data bits. Here let us, I have taken a small example of 4 data bits. That's in 1011. Now I will place them into an order. Means whereas my data bits that's in 3, 5, 6, 7 is my data bit. So in this position I have to place 3 is in 1, 5 is in 0, there's a 6 is in 1 and the 7 is in 1. That is my code word. Okay. So now coming to this fourth step. Now I need to calculate. Now I need to calculate the parity bit values. Right. I need to get the parity bits. The parity bits are no value. So I need to find out there's a value of the parity bit. So now we'll calculate the parity bit such that they cover the specific positions. It's going to be covers the specific positions to ensure the error detection and corrections. I have already told you this in the first itself. It has an error correction and as well as a detection as well. Okay, so now it's going to calculate the parity bits such as they cover specific positions to ensure the error detection and as well as a correction. Okay, so now come to this parity bit of P1, this one. So parity bit positions are 1, 3, 5, 6, 5 and 7. Only 4 data bits we need, right? This calculating the positions of 1, 3, 5, 7. In our case, we can mention this position of 3, 5, 7. 3, 5, 7. So we have to hold 3, 5 and 7. So we have to hold 1, 0, 1. 1, 0, 1. So here we need to know the value of the parity bit. So we already know this. We have to perform this XOR logic here to get this binary value, right? So I was performing this 101 with an XOR format. There's a 10, it will be a 1, 1, 1, it will be considered as a 0, right? So what is this XOR value? 00. If it is the same value, it should be 0. If it is a different value, we have to displace as a 1. right? So here also I'll get as a 0, the parity bits. So coming to this, the next parity bit, that's in P2. That's in P2. Okay. So let us see this of the P2. Coming to this, the P2 positions, what happens? P2 positions. Here you can see this P2 positions. That's in 2, 3, 6, 7. Okay. 2, 3, 2, 3, 6 and 7. Okay. 2, 3, 6 and 7. Okay. So what is the 2 value? There is no value for 2. What is the 3 value? That's in 1. 6 value 1. 7 value 1. So for the P, we are going to positions of 3, 6, 7. That's in 1 and 1 and 1. So I have gone through with an parity 1, 1. It will be considered as in 0. 0 XOR 1. That will be considered as in 1. Okay. So please check one. Okay. 1 plus XOR of 1. Same means we have to consider as a 0. So now this 0 was performing an XOR operation for 1. Okay, that will be considered as a 1. Right? So we got this P2 position, the value is in 1. Okay. So coming to this P3 value. That's nothing but a parity bit. Third parity bit with the value of P4 we are mentioning here. Right? So coming to this P4. The parity bit positions are 4, 5, 6 and there's a 7. 4, 5, 6, 7. That's a parity bit positions. So now we have to calculate the parity for the positions of 5, 6 and 7. We have to calculate the positions of 5, 6, 7, 7. That 5, 6 and 7. That's a parity bit falls is in 0, 1, 1, 1. That's a 0, double 1. So now if I perform as a XOR logic gate here, that's a 0, 1. 0, 1 means that will be a 1. And 1 and 1 that will be considered as a 0. Okay. So now P4 value is a 0. Right. So now construct the final code word after calculating the parity bit. The final code word is an here P1. P1 is an 0. Right. P1 is an 0. P1 is an 0. P2 is an 1. P3 is an 0. Sorry, 1. P4 is an 0. P5 is an 0. P6 is an 1. P7 is an 1. So now my 7-bit data is an 0, 1, 1, 0, 0, 1, 1. This is my code word. Now this code word I have to transmit it to the receiver. The receiver will take this code word and will perform this same thing, decoder in the reverse format. In the reverse format. So after that it will be get this a virtual data. It will be gets us virginal data. Okay. So let me go through with the last slide. Okay. It will be mentioned as a virginal data. So this is about our Hamming code, how this going to be performed. Okay. This is our code word. It's going to be transmitted and we are going to get this out. Fine. So this is our Hamming code. Fine. So if you have any doubt, so please let me know. Fine. Okay.